Hello, everyone. In this lesson, I like to, because this is right after the implicit differentiation that we did. And now it's time to apply implicit differentiation to derive logarithm related or situation that logarithm will make easier to take derivatives, to find derivatives of functions. First of all, we recall that we have the derivative for b to the power x. Okay, note its difference. Okay, note the difference between the derivative of x raised to the power of n. So I hope you guys know the difference. The difference is that in the first case, b is the constant. In the second case, the exponent is a constant. In the first case, differentiating with respect to the exponent. The second case is differentiating with respect to the base. So the latter equals to n to the power of n minus 1, as we know. But in this recording, we probably will not use this very much. Even if we do, we must know the difference. We must know the difference. Let's start with the first example. Okay, the first example is to derive the derivative of log base b of x. Okay, and of course, according to the the definition of logarithm and exponential, b is larger than 0 and not equals to 1. Okay, in this regard, it's been very consistent in the study of this function. All right, so now in order to derive the derivative of log base bx, we are going to assume that y is equals to that. Okay, by definition, of course, we want what is wanted. We want dy dx. And y is logarithm base b of x, right? So from this relationship, we know by definition of logarithm, okay, this expression will take us to b raised to the power of y. That should equals to x. Okay, y power b equals to x. And we're going to differentiate. We're going to differentiate this function, this equation, okay, implicitly. Okay, we want to get dy dx. So that's the goal. So we're going to take derivative on both sides with respect to x. Okay, so we're taking derivative on both sides with respect to x. The right-hand side equals to 1. The left-hand side, we're going to apply implicit differentiation or chain rule, right? So the right-hand side equals to 1, and we're going to focus on working on the left-hand side. So derivative of dy, we're going to differentiate with respect to y, and then dy dx. So dy dx is going to be what we're looking for. For the first part, the derivative of b to the power of y with respect to y, we can apply this formula. So when we apply that formula, of course, it's going to be derivative, derivative with respect to y. So this is a b to the power of y ln b, right? So in our case, by applying that formula, we got the letter in the bracket. Okay, I'm going to take this piece and substitute the derivative of by with respect to y, and then still multiply dy dx, and that equals to 1. And next, we're going to solve for dy dx. dy dx. Okay, because we know ln b is going to be, b is not going to be 1. The b is not 1, so ln b will not be 0. B to the power of y is always positive, so we can divide both sides by b to the power of y multiply ln b on the other, and we get this piece. So that's what we are very close to. But b to the power of y, b to the power of y is equals to x. So at this moment, we can replace b to the power of y by its equal, which is x. Okay, so by this time we have derived this formula. We'll derive this formula. Okay, so far from here, right, we got that piece. We got that piece. Okay, and example number two actually is actually a simple application of the formula we just derived, right? Since we have the derivative of log base b of x, now that b is the base is greater than 0, not equals to 1. Therefore, we're going to replace b by e. So this is the new one. Of course, log base e is ln, and ln e equals to 1. And anything times 1 stay the same. Right? So this is how we got the derivative of ln x with respect to x is equals to 1 over x. Okay, so we got this formula as well, right? It's a very useful one. So we're accumulating our useful formula now. So what we're going to do is I'm going to take all three. Okay, we're going to work on example number 3. We need to find dy dx, right? So this is going to be a derivative, dy dx. So we're taking derivative of ln x raised to the power 3 plus 1. And we're going to write that by chain rule, right? So we assume this is u, right? So this is a du, and then du dx, du dx. And the derivative of ln u with respect to u, the derivative of ln u with respect to u, right? So we're going to apply that formula, except it is on u. It is on u. So if these two were u, the result is will be 1 over u. So that piece is going to be, okay, the derivative ln u with respect to u is going to be 1 over u. And the derivative of x raised to the power 3 plus 1, that's going to be 3 times x squared. Okay, So in the end, right, because u is an intermediate variable we introduced. So in the end, we're going to bring u to our expression, bring u back to our expression. Oops. So the u should replace just the denominator. Okay, we don't need that parentheses. And if you like, you can put this on, you can put this on the top. Same thing, no problem. Now by this time, right, we have ln of something. In fact, if we have the derivative of ln u and u be any function, okay, u be any function of x, then we can apply the same chain rule, right? This just makes this du and then du dx, right? That's how we get, and that piece is 1 over u, like we did earlier. So this is going to be 1 over u. You don't need to memorize these formula, but if you derive it just once, you get it. Okay, if it doesn't get it by doing once, do it another time. Okay. Wait, so I meant to put this formula next to it. Okay, but you don't really need that formula. The only thing you really need to know is this one. Or you can derive all by yourself. Okay, if you know this piece, you can derive everything all by yourself. So please do the deriving. Please do the deriving. And this formula, okay, is basically assuming u is g of x. So we get the same formula. And this other formula can also be written as the derivative gx with respect to x, that's a g prime. So you can write it that way. But once again, I'm not promoting the memorization of these formula. Okay, really. Okay, I just want to show you, and I hope you're deriving with me. Okay, you're deriving with me so that at least becomes, pretty easy for you. Okay, that's really the only way and the best way to get around this. So now with all of these formula with us, right? So we now have a bunch of formula. Let's try not to bring any one of them with us. Just apply the chain rule. Okay, look at number 4. Look at example number 4. We want to find the derivative of f of x, right? So the derivative of f of x, f prime. So we first treat it as root u, right? Square root of u, with ln x is a u. So we're going to use the chain rule, okay? So the derivative, okay, so let's write it down this way. The derivative of the square root of ln x, so we're going to take that piece, okay, make it the u, and this is a u, multiply, and then du dx, du dx, du dx, and u, of course, is ln x in our case. And what does this equal to? The derivative of u, in fact, this is the square root of x, right? So we know of square root of x. Derivative with respect to x, square root of x. Right? We know the derivative of this function, that's equals to 1 over 2 times square root of x. Oops, there. Okay, so when we're looking for the derivative of square root of u with respect to u, so this becomes u, this becomes u, so this becomes u. So this piece is equal to 1 over 2 times 3u. Multiply the derivative ln x with respect to x. We know that's 1 over x. Okay, so that part you don't have to show. Okay, I'm just showing you. Okay, last but not least, we need to bring the u back. Okay, so it's 1 over 2 times square root of u, and u is ln x. And multiply 1 over x. If you like, you can write this x to multiply with the denominator of 2x under 2x like that. Okay, that's it. Number 5. Okay, let's look at number 5. Number 5, we have a common log. We want to find the derivative of x. Okay, and of course, by this time, we already have this formula with us. Okay, so let's see how we're going to do the substitution here. Okay, so we're going to apply the formula here. Okay, this is the formula we're going to use. So we're going to take a derivative with respect to x, right? F of x. And or, right? That means f of x is really the log of that. So what we're going to do is that we're going to take, of course, we're going to apply chain rule. So the derivative of a log, this is our u, du. Multiply du dx. That's du. Okay. And of course, you could have done your faster version of this, but I'm just going to be cautious. Okay. Common log u. So that's the base e. I'm sorry, base 10. Okay. So applying this formula, right, you can see this u and that u match. So we have this x and that x match. Now it's u. Everywhere x changed to u. Okay. But base 10, right? So this is called this ln 10. And common log base 10 by default is that. So du, the derivative of log u with respect to du is 1 over u times ln 10. So that's what we need here. Okay. So we're going to replace it. Replace this part by that. And then, of course, we need to finish up the differentiation of 2 plus sine x. The derivative of 2 is 0. The derivative of sine is cosine x. Okay. And in the end, you could have just put it on the numerator like that. Done. Okay, it's finished. Number 6. Number 6, there are actually 2 ways to do it. There are 2 ways to do it. Okay. One way is just to go it straight. Go straight. Okay. And we're going to take derivative. Oh, sorry. In the previous question, I forgot to substitute the u back. Okay, so let's one more step. Okay, sorry about that. U will be substituted back by what u was, right? That's 2 plus sine x. And that's the end. That's the end. Okay? And now we're going to assume this piece is ln u. So this is our u. So du, and then we're going to multiply du dx. Du dx. Okay, that's our u. You can see we're going to apply quotient rule here, right? The first part, we're already pretty familiar with this part of the logarithm part. That's just a 1 over u. Okay, if you like to bring the u back, you can bring the u back here. Let's do a next step. I'm going to differentiating this part. So that's going to be quotient rule. So square root of x minus 2 squared. And differentiating x plus 1, that's 1. 1 multiply the square root of x minus 1, subtracting. We're going to keep the x plus 1, differentiating the square root of x minus 2. So that's going to be 1 over 2 times the root of x minus 2. Okay. On the next step, right, if you like to bring the u back to where you substitute u by its equal, you can do that. Then we have a complex function situation. We have a complex function situation. So what we can do, we can take care of this part. Okay, you can do your normal complex fraction in many ways, in at least 2 ways. But what I'm going to do is I'm going to take care of this part. So root x minus 2 will be flipped up. So in the denominator is just x plus 1. And I'm going to take this root x minus 2 to multiply this top. Okay. And that's what I'm going to do. So I'm going to multiply that on 2 terms. So this piece, okay, multiply that. That would turn into squared. I multiply the second term, I got this. And root x minus 2 and root x minus 2 will reduce. And of course, we have a 2 here. Okay, but let's not worry about it too much. Okay, we'll get there. This piece is just x minus 2. Okay, the latter part, now you can kind of take care of the 2 because the fraction 2 is a little bit cumbersome, right? So you're going to multiply the top by 2, the entire top by 2, right? So this is multiplied by 2. This is multiplied by 2 becomes 4 times 2, that's 1, right? The denominator needs to be multiplied by 2 as well. Okay, that should make sense. And simplify, we get subtract x, subtract 1. And 2x minus x, that makes 1x, right? So we got 1x, right? Take away this, and minus 5. I think that's it. That's it. Finish. Oh, here. Root of x minus 2 squared, that's really just x minus 2 twice. So that's really just x minus 2. In fact, we could have done that much earlier. Okay, so let me just do the substitution here. We could have done it earlier, right? We could have done it earlier. Oh, we could have done it much earlier. Like that. Okay. If you don't want to substitute the last one, then we can keep that one. Okay, that's it. And if you want to rewrite it, I say, okay, I want to write it as a one fraction form. So that's x minus 5. So you have 2 times x plus 1. You can see this way actually is rather long. We have another way we do. Okay, so we got this answer. And that equals to this piece. We actually have another way to do it. Another way to do example number 6. How do we do that? Okay, we're going to apply quotient rule. Okay, quotient rule of logarithm. What is the quotient rule of logarithm? Quotient rule of logarithm says if we have log base b greater than 0, not this is a capital A, this is a capital B. Okay, if we have any base larger than 0, not equals to 1, and we have A over B, and that can be written as 2 other logarithm in subtraction. And capital A goes here, and capital B goes here. That's quotient rule. So if we apply that, you will see our work becomes much easier. Okay, much easier. So we're basically taking derivative of a difference. Okay, so we have ln x plus 1 subtracting ln root of x minus 2. If we apply power rule of quotient of logarithm, right? What is the power rule of logarithm? Oh, sorry. Power rule. Why doesn't change? Okay, I need to change to a different mode. Power rule. Okay, power rule says for any base, okay, if I have say, I'm going to use an interesting symbol. Okay, I'm going to use omega to the power of, let me use k. Okay, it's a power. Then I can bring the power down with the logarithm base b omega. So in our case, natural log root x minus 2 can be seen as, okay, it can be seen as x minus 2 raised to the power of half. Raised to the power of half. So we can bring that power to half down in front of ln. So now we're differentiating these two. You can see it is expected to be much easier. okay? And of course, we still have to apply chain rule, but we're gonna differentiate separately, okay? So inside the bracket, we're basically differentiating two separate, okay? The constants can be left outside. We're differentiating like this. You can see it's much simpler, right? You can, you probably even prefer that. So what is the derivative of ln x plus 1? Well, that's just going to be 1 over x plus 1, and chain rule of differentiating x plus 1, that's the derivative of x plus 1 is 1, okay? Minus 1/2, and ln x minus 2, and that's going to be x minus 2, oh sorry, x minus 2 should be under 1 over x minus 2 times 1. The derivative of x minus 2 is 1, okay? So that's all we get. But the question is, we have a different looking answer, right? So can we make them the same? Okay, of course, we must try to make it same. Otherwise, we may have some doubt, right? So let's do that. Let's do it. So the common denominator obviously is going to be 2 times x plus 1, right? Times x minus 2. That's our common denominator, right? So that's our common denominator. We're going to make them the same common denominator. X minus 2 inside parentheses, forgive me, right? So from here to there, right, we have multiplied 2 times x minus 2. So this is going to be 2 times x minus 2. Boom. The second one, we have 2 times x minus 2 before, so all we multiply is just x plus 1. So we got the same denominator. We got the same denominator. So we're going to keep our same denominator. We're going to keep our same denominator. On the numerator, we're going to do 2x minus 4. Now minus x minus 1. Okay, let's see if we get what. Okay, well, let's see what we get. Keep the denominator, 2x minus x, that's going to be x, right? X minus x. And this is a minus 5. So it looks like it's exactly the same. And of course, by this point, you have a preference. Which one is easier? Which one is easier? All right, we have 2 more to go. On this one, we like to have a good discussion about ln x in absolute value. First of all, we look at this function. What is this function, right? What is the domain, right? We should be most concerned about this domain because ln x, you know, whatever is being taken ln x must be positive. So the domain is going to be satisfy this condition, greater than 0, greater than 0. But we know that absolute value of x is always greater than or equal to 0. So this will lead to our domain to be x is not equal to 0. i.e., x may be negative, x may be positive. The only number that x cannot be is 0. Okay? Now you wonder how this function looks like, even though it is not essential for us to know the graph, but I think it's interesting to know the graph. Okay, so this is the graph of this function ln x. It's like, they're like 2 wings of a bird, right? And is basically an even function of ln, so you have ln x flipped over, right? So what are each piece, right? What are each of the pieces? So if we apply this, right, the absolute value, if we apply absolute value, right, and now we don't want x to be equal to 0, so we have two pieces, right? If x is larger than 0, then the absolute value of x is the same as x. Excuse me. If x is negative, then the absolute value of x is the opposite. But if we apply this piece, right, and we can write ln absolute value of x in two pieces. In other words, when x is larger than 0, it's going to be just ln x. And in case ln is less than 0, it's going to be ln of parentheses negative x. Okay, so now we're going to take a derivative. We're going to take a derivative to prove, right? Is this true? Right, so we're going to prove if this is true. So we're going to work on these depending on if x is positive or negative. So if x is positive, that's a trivial, right? For x is positive, the absolute value of x is x. So on this piece, it's going to be just that. And we know what that equals to. That's 1 over x. We got that. We knew that before. But what if x is negative? If x is negative, the derivative of ln absolute value of x is equal to the derivative ln x. The absolute value of x now is replaced by negative x. And then we take a derivative, right? And we don't have to go by its chain rule. So this is going to be ln u. Our u is the parentheses absolute negative x. So that's the u. And then the derivative of negative x dx. So that's what we have. And the former, right, the former is just 1 over u. 1 over u. 1 over u. But what is u? U is negative x, right? U is negative x. And what's the derivative of negative x with respect to x? It's negative 1. So in the end, we still get 1 over x. So in either case, okay, for x greater than 0, the derivative ln absolute value of x is 1 over x. For x is a negative, the derivative absolute value of x is 1 over x. And that's why we have this formula. So regardless, right? So this is true for, and of course, for x is not equal to 0, which is in the domain of the function. This formula is worth noting because we might be using it quite so often. Okay. All right. Number 8. For number 8, if we're differentiating this function, it's going to be rather complicated, okay? Because we have done the derivative of that function. It already showed some complication. But this time we don't have a logarithm, but we can do the following. We can introduce logarithm, okay? So we're going to take ln y equals to, so we're going to take a logarithm on both sides. We're going to take a logarithm on both sides. And then we're going to apply product rule, quotient rule, power rule as we wish. And we also then, so I'm going to take product rule, quotient rule. Okay, product rule, quotient rule. This we only have a quotient rule. I'm going to write down the product rule. The product rule. Oh, come on, I don't like this. Okay, product rule. What is a product rule? Product rule, of course, is about product. Base B, logarithm base B, capital A times B. Okay, and this equals to a single logarithm on a single logarithm on B, but instead of subtracting in the quotient rule case, we're adding. Boom. So this is our product rule. Once we have these 3 rules, we can apply them. So here we got a quotient, we got product, so we can do ln, right? X raised to the power 3 quarter plus ln the root subtracting ln the whole of the denominator. And then we're going to apply the power rule. Applying power rule, 3/4 is going to be brought down. And ln x plus the root is 1/2. And we got ln of x squared plus 1. Subtracting 5 times ln 3x plus 2. All right, so we got ln y equals to all of these in a much simpler logarithm form. And of course, next we're going to take a derivative. So this is going to be implicit differentiation. Okay, so to take a derivative on both sides on every term. So we can just work on the part with variable derivative. So that's 2 separate derivatives. On the left-hand side is going to be derivative ln y, dy, and then dy dx. Okay. Oops. Sorry. This is dy dx. On the other side, right, we're going to do it 1 by 1. So 3/4, right? So that derivative, this piece is just 1 over x. And the second piece is 1/2. We're going to apply chain rule. We're going to apply chain rule. So it's 1 over x squared plus 1. X squared plus, x squared plus 1. And multiply 2x. 2x. The last term, 5, is going to be the derivative of ln of 3x plus 2. So it's going to be 3x plus 2, and the derivative of 3x plus 2 is a 3. So by this time, we have, moved forward. And this piece, of course, we know that's just 1 over y. Multiply dy dx. And the right-hand side, we're just going to do some organization. And that piece is 3 over 4x. And the second part, this 2 and the other 2 will reduce. So the second term will be just x squared plus 1 under x. Last, okay, 3 times 5, that's a 15. So we got a 15 over 3x plus 2. By this time, we can multiply y on both sides. So then dy dx will be solved. So y multiply all of these. There. Then you say we have to bring back the y, right? Yes, we do. We're going to bring back the y. The y is the whole of that. Boom. Finished. Finished. Now you may wonder, is there room to reduce? You can try it. You can try it, but in my observation, I think it's better we just leave it like this. That's all for this time. Thank you for watching.